To understand an internal combustion engine, we have to look past the complex machinery and start with its absolute core function. It exists to convert rapid, violent chemical expansion into usable mechanical torque. Creating a single, controlled explosion inside a metal box is simple. The engineering challenge arises when you repeat that process thousands of times every minute. Without intervention, that relentless sequence of detonations quickly melts the surrounding metal infrastructure. Preventing the machine from destroying itself requires a synchronized orchestration of subsystems. It relies on precise fluid dynamics, millisecond-perfect electrical timing, and an aggressive thermal management network to bleed off extreme heat. We are going to construct a modern high-performance engine from the ground up. We will start with a single, isolated piston, build out the survival networks it needs to function continuously, and conclude by examining how modern designs, specifically the structural optimizations of the BMW B58, push these physical limits. A modern car engine functions as a complex, interdependent ecosystem of survival subsystems wrapped tightly around a thermodynamic core. The foundational architecture of power generation begins with a single, isolated piston housed inside a cylinder. This is the base unit of the engine. This diagram shows the first phase of the cycle, the intake stroke. As the piston descends, it creates a vacuum in the chamber, drawing in a precise mixture of air and fuel through the open intake valves. Next is the compression stroke. All valves close and the piston ascends. This highly pressurizes the trapped mixture, making it dense and volatile to amplify the energy of the upcoming combustion. Then comes the power stroke. A spark plug ignites the compressed mixture. The resulting explosion violently forces the piston back downward. Out of the 4 steps, this is the only stroke that actually generates power. Finally, the exhaust stroke. The piston makes one last upward movement, pushing the spent gases out through the newly opened exhaust valves, clearing the chamber to start the cycle again. The piston moves in a straight line, up and down. To be useful for driving wheels, this linear force acts on a connecting rod, translating vertical thrust into continuous rotational energy of a crankshaft. When you see the term RPM, or revolutions per minute, it specifically measures this movement. It is the exact count of full 360-degree rotations the crankshaft completes in 60 seconds. A single piston executes this cycle perfectly in isolation. But its intermittent power delivery, providing thrust only once every 4 strokes, means it must be scaled up and sequenced with others to drive a heavy vehicle smoothly. To eliminate the gaps in power between individual strokes, engineers link multiple pistons to a single crankshaft. As one piston resets, another is firing, overlapping their power strokes to deliver smooth, continuous torque. This sequence is dictated by a specific firing order, like 1-3-4-2 in a 4-cylinder layout. Because the sequence generates violent alternating downward forces, the crankshaft uses heavy counterweights to balance the momentum and prevent the rotating assembly from shaking apart. Looking at this breakdown chart, we can see how modern manufacturing uses these base units. Instead of engineering entirely different engines from scratch, automakers use a modular architecture, duplicating a single standardized cylinder to create different engine sizes. By standardizing a single cylinder to a half-liter displacement with an 82mm bore, BMW shares identical parts across entire product lines. 3 of these cylinders make the 1.5-liter B38, 4 make the 2.0-liter B48, and 6 in a row make the 3.0-liter B58. High parts commonality yields a significant economic advantage. By sharing identical pistons, forged connecting rods, and valve train components across different blocks, automakers drastically reduce their research, development, and production costs. However, solving the problem of continuous power delivery by adding more cylinders directly multiplies the friction and thermal output of the machine. To keep this scaled-up metal block from seizing, fluid survival networks must be introduced immediately. The first existential threat to a running engine is extreme mechanical friction between tightly fitted metal components moving at high speeds. This cross-section illustrates the pressurized lubrication pathway. An oil pump draws fluid from the reservoir in the oil pan at the bottom, forces it through a filter, and pushes it up into the internal galleries, coating the moving parts to prevent metal-on-metal contact. At the piston level, grooved metal rings serve a highly specific function. They sweep the cylinder walls to maintain lubrication while creating a hard boundary that strictly blocks that oil from passing upward and contaminating the combustion chamber. Once friction is mitigated, the engine faces its second and more destructive existential threat, the rapid accumulation of extreme heat from the constant explosions. A water pump drives the primary coolant cycle to extract this heat. It forces a mixture of liquid antifreeze through internal water jackets, wrapping entirely around the cylinders, absorbing the excess thermal energy directly from the hot metal. A thermostat acts as the system's gatekeeper. Once the coolant reaches maximum operating temperature, the thermostat opens, routing the boiling liquid into the radiator. There, it passes through a network of small tubes and fins, shedding its heat into the oncoming airflow before circulating back into the block. These interacting fluid networks create a fragile equilibrium, but as performance demands introduce forced induction and higher compression, they push traditional engine block geometries past their physical breaking point. In a standard open-deck engine block, there are large hollow channels around the cylinders to maximize coolant flow. This split screen compares standard geometry against the BMW B58's closed-deck block design, an architecture derived from heavy-duty diesel engines. Instead of wide gaps, the top of the B58 block is a solid aluminum deck with only small, precisely drilled holes allowing coolant to pass through. By sacrificing some total coolant volume for sheer mass, this closed-deck geometry, combined with forged internal components, allows the cylinder walls to withstand vastly higher combustion pressures without warping under the load. The B58 also introduces an external thermal encapsulation system. Instead of relying solely on internal fluids to manage temperature while running, it uses advanced external insulation to manage temperature while the engine is turned off. This insulation retains internal operating temperatures for up to 36 hours after shutdown. When the vehicle is restarted the next day, the engine is already warm, which reduces cold start metal friction and lowers startup emissions. Internally, the B58 structurally integrates the exhaust manifold directly into the water-cooled cylinder head, rather than bolting it to the outside of the block as a separate metal component. This integrated design serves two efficient purposes. Extreme heat of exhaust gases routing through the cylinder head speeds up coolant warm-up times. Simultaneously, it positions the turbocharger close to the exhaust ports to reduce turbo lag. Modern performance engineering demands geometrically superior metal structures to securely cage violent expansion while retaining thermal energy as efficiently as possible. Once the power is generated and the thermal energy extracted, the spent exhaust gases leave the optimized block. They flow into the catalytic converter, which chemically strips out toxic elements before passing through a muffler and exiting the vehicle. None of this mechanical hardware functions without an unseen conductor. The Engine Control Module, or ECM, constantly monitors the entire ecosystem, recalculating spark timing, air-to-fuel ratios, and fluid pressures millisecond by millisecond to ensure perfect synchronization. From a single piston moving through a simple four-stroke cycle to the complex, closed-deck, thermally encapsulated power plants of today, the internal combustion engine has evolved into a highly optimized machine. The resulting machine is a rigid, meticulously fluid-cooled architecture that translates destructive thermodynamic chaos into continuous, reliable forward motion.